Well, there are different operations on sheet metals, and we are going to do a number of problems on each of these operations. The two equations on this slide are the ones to be used for shearing or cutting operations. The first equation is making it possible for us to do the computation of clearance, the clearance between the punch and the die. If we take a close look at it, look at this figure here, we can see that there is a size difference between the opening of the die and the size of the punch, and this is referred to as clearance. If this is a round punch, then there will be 2c, that is the difference between the two. In punching operation, when we are just going to make a hole on the actual workpiece material, it is the size of the punch that is of importance, and that is the one that will be left on the workpiece. But if this is representing a blanking operation, then what is coming out of the die opening right here is the desired part. So it is the size of the die opening that is deciding the size of the workpiece material. So we should be careful in applying the clearance to the punch or to the die as needed. In order to do the computation of clearance, we need to know the thickness of the sheet metal, that is T, and clearance allowance AC. The value of clearance allowance depends on the quality of the workpiece material, and there is a table that is provided in the lecture notes. When we know the quality of the sheet metal, we can take the value of AC out from the table. We will use this in the problems to see how it can be done. Next equation is the equation providing us with the possibility of computation of the cutting force in sheet metals, and that is equal to shear strength times thickness times length of cut. Length of cut is the perimeter of the punch. If this is a round punch, then L will be equal to circumference of the punch. So T times L is giving us the shear area, and S is of course shear strength. Problem 1. A blanking operation is to be performed on a 2 mm thick cold rolled steel half hard. The part is circular with a diameter of 75. We are to determine the appropriate punch and size and die sizes for this operation. Well, let's take a look at the figure that we had in the previous slide again. As we can see it here, well, there is actually a clearance, which is the difference between the punch and the die on each side. And because this is a blanking operation, what is coming out of the die opening is the actual part, which is this. So the size of this blank is important, and this is decided by the size of the die opening. In order to make this to the desired size of 75, we've got to make the die opening to the actual size of 75 and make punch smaller by 2 times of C. So we need to compute C first, and this is the table for clearance allowance. When we know the quality of the workpiece material, which for this given case it's cold rolled steel half hard, then the value of AC is 0.075. Now by making use of the equation for clearance, which is also given here, if we substitute this value into in this equation and also substitute the value of T, which is given to be equal to 2 mm, then we can easily get the value of C. So AC times T, 0.075 times thickness, which is 2, is giving us clearance for this given operation. Of course, as I mentioned, the difference between the size of the punch and the size of the die is 2 times of C. So the size of the die will be the same size as the desired part, 75, and taking 2C out from this is giving us the size of the punch. Next problem. Well, we are to determine the blanking force required in problem 1 if the shear strength of the steel is this much. And tensile strength is also given. Taking a look at the operation, this is a shearing operation. What we need to do the computation of the force is F is equal to shear strength times say thickness times length of cut. Length of cut is circumference of the punch. So what we need is only shear strength, and we don't really need tensile strength. So this isn't needed. Okay, first we do the computation of L, and that is the circumference of the punch in this given case. So uh, operation is blanking. Thickness is 2 mm, blank diameter is given, shear strength is given, tensile strength is given, but this is not needed. So we have to compute blanking force. And then by making use of this equation, we do the computation of the circumference first, and then shear strength times thickness times uh, L, which is the length of the cut, is giving us the force needed for cutting. Please note that this is minimum force for cutting, so when the sharp is when the cutting tool, that is in this case it's punch and die, are sharp, this is sufficient. But as the die is being used, it will not be as sharp as it was in the beginning after a number of cuts, so this force gradually will increase. So it is safe to add some 10 to 20% to this force, making sure that we are on the safe side, and when the punch and die are not sharp, they are still capable of cutting the sheet metal. Okay, on this slide we have got two equations for bending operations. First equation is making it possible for us to do the computation of the bend allowance, AB. What is it? If we take a look at this figure on the right, we can see that there is a sheet metal that is bent. Some certain sections of it are straight before and after bending. But the area of the material which is within the bend angle, there will be a difference in the, say, initial length of it before and after bending, and this bend allowance is making it possible for us to do the computation of the bend angle when it was straight before bending indeed. This equation is helping us to compute the length of this bend angle when it is straight before bending. In this equation, what we have got is R, which is the bend radius. Right here in the figure, we can see what it is. And we've got alpha, which is the bend angle. Alpha, we can also see it, what it is here. And we've got also thickness of the sheet metal, T, and there is a coefficient, KBA. KBA is a factor to estimate stretching. Its value depends can be computed from this equation. If R, which is the bend radius, is smaller than 2 times of thickness, then the value of KBA is 0.33. Otherwise, it is 0.5. Indeed, it is the representation of the neutral axis, this axis here. When R is smaller than 2t, then this neutral axis gets closer to the inside radius. Otherwise, it stays in the center or close to the center. So it is a representation of the position of the neutral axis. There is another equation for computation of the force in bending. Well, in this equation, we've got KBF, the value of KBF, bending force coefficient, depends on the type of the bending die we are using. For V bending dies, this one, the value of KBF is 1.33, and for edge bending die, this one, the value of KBF is 0.33. Well, we've got some other parameters in this equation. TS stands for tensile strength. Of course, this is a bending operation. We are not cutting the material, so instead of shear strength, we are in need of, say, tensile strength. W, which is the width of the sheet metal. You can see in this figure here what is meant by W, width of the sheet metal which is being bent. And T is the thickness, and D is the distance between the two supporting points on the die. As you can see, it is shown down here what is meant by D in V die, and also similarly what is meant by D in edge die. Two supporting points on the die or on the die and the punch in bending operations is actually referred to by D, or it is referred to as die opening. Okay, moving on. Problem 3. A bending operation is to be performed on 5 mm thick cold rolled steel. Determine the blank size. Well, as we can see in bending operations, what we are provided is the actual drawing of the sheet metal after it is bent. The task of us is to be able to compute the length of it when it is straight before bending, so that once it is bent, this part is achieved. As we can see, we can divide this shape into three sections. Two straight sections of 45, 46.5 and 58, and a section within this region, within the bend angle right here. We've got to be able to compute the length of the neutral axis within the bend angle and add this to the two straight sections in order to get the size of the sheet metal before bending. So what we do is to write down what we are given. Operation is bending, thickness is given, type of the material is also provided, and we are to determine the length of the sheet metal, which is also given. So the length of it is to be computed when it is straight. In order to do that, what we need to do is to make use of the equation for bending as it was provided in the equation sheet, this one. And uh, the bend angle here, alpha, as we take a look at this, the bend angle alpha is the angle of bending that is to be applied in order to get this part. We have got an angle here, an angle of 40 degrees that is given here, but this is the actually included angle on the workpiece material. In order to convert a straight sheet metal to this, we need to apply an angle of 180 minus 40, and that will be the actual angle, bend angle of alpha that is on the workpiece material. So A will be 180 times 180 degrees minus alpha prime. Alpha prime is what is provided here, right here. Alpha prime is 40, so the difference between 180 and 40 is 140, and that is the actual value for alpha that is to be applied. So we've got the value of alpha now. R is provided in the drawing. We have it right here, 8.5, and then thickness of the sheet metal is also given in the statement of the problem. It is 5 mm. The unknown parameter KBA, bend angle constant or coefficient, is it depends on whether it is smaller than 2 times of T or greater. Thickness is 5, 2 times of C is 10. So R, which is 8.5, is clearly smaller than 2 times of T. So on the basis of what we had on the equation sheet, the value of KBA is now known. So R is smaller than 2 times of thickness, and then KBA will be equal to 0.33. Now we have got everything to be able to compute the length of the bend angle. We substitute all the parameters, and then what we get is AB, and that is equal to 24.84. Now, in order to be able to compute the initial length of the part when it is straight, we need to add this value to the two straight sections of 58 and 46.5, and that is giving us the total length of the part when it is straight. The width of the part is also given in the drawing. Problem 4, determine the bending force required in problem 3, the previous problem. If the bend is to be performed in a V die with a die opening or D. Die opening or D is also given here. Well, this size is given is 40 D. The material has a tensile strength. Tensile strength of the material is given. This is needed in bending operation. and a shear strength of 430 MPa. We don't really need shear strength in this problem because we are not cutting the material, but we are bending it. So what we need to do is to make use of the equation that is provided on the equation sheet, summarizing what is provided. And then, because this is a V die, we know the value of kBa for it. So what we do is to make use of the equation for computation of the force for bending on the equation sheet. Tensile strength is given. kBf, we know what it is. It is because this is a V bending die, it is 1.33, and then 1.33 is the kBf. Tensile strength is given. Width of the workpiece material is given up here. It is substituted in this problem. Thickness is also given, and this is the die opening, of course, which is 40, and this is applied. Then we can easily compute the required force for bending of this workpiece. Problem 5 is asking us to do the same problem, except that the type of the bending die that is used is whipping die or edge bending, this one, same thing. The only difference is the value of kBf. If we take a look at the equation sheet again, the only difference in V bending and edge bending is just the value of kBf. So instead of 1.33, what we need to do is to apply 0.33. If we change the die from V die to edge bending or wiping die, then we can get it computed. Simple as that, everything else remains the same and the value of force is less. We need to know that we also need to apply actually a blank holder when we are making use of edge bending. A holding force is also needed, which is used in order to hold the sheet metal on the die when bending is in progress, and this one was not needed when we made use of a V bending die. Let's take a look at the equations for drawing or deep drawing operation when we are actually converting a disc shape sheet metal part, just like that one, into a shell, something like that. Well, we have got a number of equations for this operation. Clearance is always greater than the thickness of the sheet metal, because sheet metal has to be actually located in the gap between the die and also the punch. As we can see, the sheet metal has to stay in between. So this distance has to be greater than the thickness. Normally 10% more is sufficient. Drawing ratio can be computed if we have the punch of the blank, this one, the punch of the blank, and the size of the punch. If we have these two available, then we can compute the drawing ratio. Reduction, also if we have those same parameters, then we can compute reduction, percentage of reduction as well. Well, and there are two forces to be computed: the force of drawing, the force that is needed in order to push the part or sheet metal inside of the die opening, and also the blank holding force, FH. This is the force that is needed in order to to actually press the part in between the die and the top face of the die and also the blank holder. This force has to be adequate. If it is less or more, we produce defective parts. So it has to be computed, and the right force is to be applied for blank holding. Well, in the equation for force, we have got dP, which is the punch diameter, T is thickness, stands for tensile strength, dB is actually blank diameter, dP is punch diameter, and zero point 0.7 is a correction factor for friction. For holding force, we have got yield strength, Y, which is yield strength, dB we know what it is, dP we know what it is, and RD is the radius of the die. If we take a close look at this figure here we can see that the actually die is not sharp. There is a radius here which is applied because we don't want to cut the material, we want just to push it into the die opening, so we make it round, and this radius is of importance when we are doing the computation of blank holding force, and radius of the die is sitting here in this equation. Okay, moving on to the next problem. A cup drawing operation is performed in which the inside diameter is this much. This is indeed the punch radius, dp, and the height of the shell is also given. This is the height of the shell after it is actually drawn into the die opening, which is h. The stock thickness T is 3 millimeters. The starting blank diameter is 150 millimeters. This is dB, and thickness is T, of course. Punch and die radii R, D, and RP are given to, these are equal to 4 mm each. They are equal. Tensile strength is given. Yield strength is given for this given material. We are to determine drawing ratio, reduction, drawing force, and also blank holding force. We're summarizing what is provided to us. Cup inside diameter or punch radius is given, thickness of the sheet metal, cup height is given, radius of the punch and radius of the die are equal, and that is equal to 4 millimeter. Tensile strength is given, yield strength is given, and we are to compute drawing ratio, reduction, force of drawing, and force of blank holding. By making use of the equations that we have on the equation sheet, we can easily compute, divide, say, diameter of the blank by diameter of the punch, which is giving us a drawing ratio, and that is to be less than 2 millimeter, 2, to make it a feasible operation, and that is feasible indeed. Reduction, by substituting the diameters of the blank and the punch, we can also get it computed, and this has to be less than 50%. So this is representation of the feasible operation. As well, by making use of the equation for cutting, for drawing force, we have got everything that we need as it was explained on the equation sheet. We substitute the values, and that is giving us the required force of drawing, which is 354,418 newtons. Everything is provided. Similarly, we can just substitute the values as needed in the equation for blank holding. Everything is provided in the statement of the problem. All we need to do is to substitute these values, and that is giving us the required force for actually blank holder. So the press machine that is being used for this operation has to provide us with the sum of these two forces in order to be able to proceed with this operation. Normally, it's safe to add 10 to 20% to this force when we are selecting the pressing machine. Add the values of say drawing and also holding forces together, and on top of that, add an extra 10 to 20%, and it is actually recommended to make use of hydraulic presses in drawing operations, so that the force is being applied gradually by a hydraulic actuator. And that's it for today. Thank you very much, and all the best.